Hello, on behalf of Sigma-HSE, thank you for joining us for our webinar today. We want to give everyone an opportunity to jump into the session, so we will get started in about 2 minutes. Hello again, everybody. Thank you for joining us today for our webinar on safety instrumented systems. I am Mark Yukich, U.S. Technical Development Manager at Sigma-HSE, and I will be your host today. I have nearly 10 years of process safety industry experience. That includes combustible dust, flammable vapor, and chemical reaction hazards, and steps to mitigate those hazardous materials while in process. I make it my goal to understand the pain points for our customers related to process safety. If we don't have the option to assist, I want to ensure we hand you off to a team we trust to bring value to your safety team. Please feel free to contact me should you need any assistance. Sigma-HSE is a global engineering firm with technical experts supporting companies around the world by providing actionable solutions to protect, enhance, and optimize their process. Our goal is to allow your team to focus on what really matters: protection for your people, business, workplace, and the environment. In this webinar, we will discuss safety instrumented systems, or SIS. SIS is used to mitigate operational hazards by providing an extra layer of protection through sensors, logic solvers, and control elements. This webinar will cover standards and compliance, risk analysis, safety layers, and more. We will have time for Q&A at the end of the session. Feel free to add those questions at any time during the training, and we will address those questions at the end of our program. Doug Gruder will be our process safety consultant leading our discussion today. Doug, I will turn it over to you.
Thank you, Mark. As Mark said, my name's Doug Gruder. I have about 28 years of operations experience in manufacturing plants. Among those are EHS and process safety. One of the things that I was responsible for doing during my tenure at my previous employer was implementing safety instrumented systems. So we're going to go over some of those today. This is not at all a comprehensive discussion, but what we will cover are some definitions and the purpose of it, the applicable industry standards, and design life cycle. So we're going to go through each step and end up with decommissioning of the system. Some definitions you'll see or you'll need during the presentation are shown on this slide. SIS means Safety Instrumented System, and that is made up of safety instrumented functions. It includes the sensor, the logic solver, which is your computer, and the final control element, which is in the field. Probability of failure on demand will also be used. And safety integrity level, this is your SIL level, which is a calculation. It includes all components in the loop, and the weakest one is going to drive the final SIL level of your system. You'll also hear mention of risk reduction factor, factory and site acceptance tests. So these are some things that you will see later on in the presentation. There are a number of industry standards. I won't go through all of them here, but the important thing to keep in mind is that OSHA recognizes ANSI and ISA 8401 as a recognized and generally accepted good engineering practice for SIS. So 8401 is a ragged gap, and you should know these standards for the system you're putting in place so that you can comply and have them function in compliance with OSHA. Design life cycle starts out with a hazard analysis, moves on to an allocation of safety layers, the design of the system, the installation, operations and maintenance when the system is up and running, modification, and decommissioning. The hazard and risk analysis and the allocation of safety layers is done at the HAZOP-LOPA point. And in this system, you'll need to do a LOPA to identify the safety instrumented level required to get your company to their acceptable risk criteria. Anything that goes into a safety instrumented system should be labeled as critical equipment and treated as such. We'll get a little bit into that. Any changes after the system has been designed must be covered under management of change. The operations and maintenance and the verification steps should be part of your mechanical integrity program. Any modifications of the system should be covered under management of change. And when you're decommissioning, you have to ensure that the parts of the system that you're decommissioning do not affect other parts of your system. So to get a little bit more into the hazard and risk analysis. HAZOP LOPA, you identify your scenarios, just like you do in any HAZOP. The LOPA piece gives you how far away from the company's acceptable risk criteria you are, and also determines the SIL level you'll need on your interlocks to bring those back into compliance. So and when allocating this safety function, you list the interlocks, you determine the mitigated risk gap that you have, and then determine what acceptable SIL levels you'll need for your independent protection layers. You'll then go on to develop the safety requirements specification. And this specifies how each safety instrumented function is to be programmed in your logic solver. It'll include conditions that trigger the sensor and the response of the final control elements. Then you move on to the design and engineering phase, where documentation and fabrication of the system is done. The documentation is very important, as it gives you an auditable trail that allows independent verification. 2 steps in testing. First, the system should be tested at the integrator's facility using a factory acceptance test. The company team will review. Loops should then be fully tested when they're installed at the site during the site acceptance test. One note here is that you're also going to have to determine how often maintenance is done on the system, because this is required to maintain your SIL level. So the life cycle management, you install, commission, and validate, okay? And that's the complete loop from the sensor through the logic solver and the final control element. All of the testing must be documented. Any modifications require an MOC. And when decommissioning the system or any part of the system, you will need to do a review to ensure that it does not impact other units. Just to reiterate, ensure all changes are covered by management of change and approved. And annual testing and verification of functionality, including the whole safety instrumented function, is required. So the safety requirement specification goes through the HAZOP, the identification of the safety instrumented functions, and this is guided by the requirements contained in ANSI and ISA 84, subclause 10.3. Your safety integrity level and probability of failure on demand are shown in this table. Typically, your process control computer will have a SIL level of 1. And if you need more than that, then you're putting in a safety instrumented system. And you should probably not go any further than a SIL 2 for that. SIL 3 and SIL 4 are seldom used. They are expensive. They take a lot more verification, and they're typically used in the nuclear industry as one example. Most manufacturing sites should not need anything greater than a SIL 2. Some guidance. This is a design cookbook, okay? And it kind of gives you where the logic solver, sensors, and final control elements should be. As I said previously, most sites will be moving to a SIL 2. SIL 1 is your basic process control system. SIL 2 gives you an additional layer of protection. You're also going to have to consider failure modes. Failure modes are very important, and there are a number of different ones. They can be in combination with each other. You can have safe or dangerous failures, and they can be either detected or undetected. You want to remember that these safety instrumented systems have to be independent layers of protection to avoid common cause failures. If they're not independent, it's an indication that the design of the system was incorrect or it could have been better. The worst combination you can experience in any of these is undetected and dangerous. That means that you don't know the failure occurred, it is undetected, and the result of its failure is dangerous for personnel, the environment, or in some cases, companies, if the plant is sold out, may consider monetary losses. This is why it's so important to do testing. So redundancy. Common thought is that, well, if I just put in 2 of everything, I'll be safer. So you can see the system designations on the left-hand column. 1 out of 1 means 1 relay opens and shuts down the system. 1 out of 2 is that 2 relays are wired in series and only 1 is needed to shut down the system. 2 out of 2, both relays are wired in parallel and both of them are needed to shut down the system. 2 out of 3 is a voting system where 2 sensors out of 3 sensors need to vote the same way to shut down the system. You can also see here that 2 out of 2 has less nuisance shutdowns and than 2 out of 3, but 1 out of 2 is safer than 2 out of 3. So this is all done during the design phase of your safety instrumented system. And it is totally up to the company's risk criteria to determine which one you will be using. Sensors and final control elements fail. And you can see here that 92% of the failures are attributed to field devices, 42% in sensors, and 50% in final control elements. The logic solver is the most stable, reliable link in the system with approximately an 8% failure rate. Next, we'll go into each component and talk about that for a minute. Starting with sensors, you really don't want to share sensors with your basic process control computer. Sensor contacts should be fail-safe. That is, they should be closed and energized during normal process operation and open when there is a loss of power, shutting down the system. Transmitter signals should go to the trip state upon failure. This takes some thought. It needs to be determined by an engineering team. If the interlock is activated on high pressure, for example, the sensor should fail high. If it's activated on low pressure, the sensor should fail low. Speaking of level, if the interlock is activated on high level to prevent the overflow of a tank, the sensor should fail high, and low if the sensor should fail low. So some sensor reliability is caught on this slide here. Diagnosis improves the safety rating of the system. The use of safety transmitters, which you can purchase, which come with a SIL rating. You may want to consider redundancy in voting, but the redundant instrument should be on separate taps, separate inputs, to eliminate a common cause failure. You may want to mix up different sensor technologies. For the application of a level instrument, you may want to have your delta as one and radar, level radar, as another. And loop testing is always required. For your final control elements, again, sharing of them with the basic process control system is generally not recommended. Safety shutoff valves should be separate from control valves. And that's because control valves are not designed for positive shutoff. Loss of power should drive the device, say the motor or the valve, to its safe state. and that's determined by a team. Typically, in installations, motors will shut off and valves will close. But you may want vent valves to fail open. Continuing with final control elements, diagnostics provides and improves the safety rating of the system, and we'll see that. Smart valve positioners are recommended, and redundancy should be considered. You'll see in a minute why loop testing is required. They should remain in their safe state after tripping, that is, they should latch. And only until the reason for the trip is determined and corrected should the operator acknowledge and put the system back into operation. Some things to consider with valves are the closing speed. They must be fast enough and strong enough. And you would want them to be fire resistant. Solenoids can be a weak link, and they must latch in the fail-safe position as determined by the team. Functional testing during operation is covered under ANSI and ISA 84. Subclause 11.8 says the system should be designed for testing, and the frequency of testing is pretty important, and we'll see that in a calculation in a few slides. Subclause 16.315 says at some periodic interval, the frequency of testing shall be re-evaluated based on factors, including the history you have with the safety instrumented function and the degradation of any of the components. Functional testing after installation goes into the calculation that we'll see on the next slide and determines the SIL level of your system. Again, it has to be documented and have well-defined criteria. It's got to include the whole loop. Increased testing increases the SIL rating of the system. And each safety instrumented function, the sensor, the logic solver, and the final control element, should be visually inspected to make sure that there are no unauthorized modifications in the system. That is, each component is installed and still there as defined in safety instrumented engineering design document, or that the deterioration of the hardware has not occurred. Next, we'll talk a little about the calculation, and here you'll see why the testing interval is so important. So here's an example, and this example shows two scenarios with different testing frequencies. You can see here that if you test the system once a year, you can achieve the probability of failure on demand of 0.018. This would give you a risk reduction factor equivalent to a SIL1. For scenario B, if you tested the same system once every 10 years, you would have a probability of failure rate of 0.125, or a risk reduction factor of 8, which is a SIL level 0. So you wouldn't get any credit in a LOPA calculation if you tested once every 10 years. In summary, there are many things to consider when installing a safety instrumented system. You have to make sure that they do consist of independent layers of protection. Probability of failure on demand of the safety instrumented function, and the testing of the safety instrumented function must be considered and completed. Modification of any loops require a management change, and deactivation of the safety instrumented function or system must be reviewed to ensure that other safety systems are not impacted. At Sigma, we can help you out with your installation and design of your safety instrumented system. Our methodology will align with the applicable standards, and we offer pragmatic, cost-effective solutions without compromising safety. Next, I'll turn this over to Mark again for any questions.
Thank you, Doug. Appreciate that. Once again, if you have any questions, feel free to add them to the questions section on the right, and we can get you an answer. It looks like the first one that's here for us, Doug, is why do you need a LOPA to determine SIL requirements?
Thank you for that question. It's because only with a LOPA analysis can you determine the safety instrumented level needed to close the risk gap. A LOPA is a semi-quantitative tool. It actually gives you your mitigated gap analysis, and you use that to determine if you can be satisfied with a SIL1 or a SIL2 safety instrumented function.
All right, thank you, Doug. Another one here is, why is testing required to maintain a SIL level?
I'll refer back to slide 25 for that one, but the testing of the safety instrumented function determines the probability of failure on demand of the system. On slide 25, you could see that testing a safety instrumented function in the example once a year resulted in a SIL1. But if you went with the same system and only tested it once every 10 years, you get a SIL 0, which is not helpful in reducing your risk.
All right. Thank you, Doug. Another one here is where do you get the mean time to failure for the various components of the system?
Okay, so the components of the system are the sensor, the logic solver, and the final control element. These should be investigated before you buy the various components, and they are documented by the manufacturer. You should also keep these documented mean time to failures in the system documentation.
Okay. Thank you. Looks like we have another one here. Why do you recommend that a manufacturing facility go no further than an SIL of 2?
Anything above an SIL of 2 will require increased cost and testing. SIL 3, for example, is usually incorporated into nuclear facilities and extremely high-risk processes as such. So it really comes down to cost and testing, Mark.
All right, thank you. And when it comes to the team, what team do you recommend when putting together a SIS?
Having worked on a number of these teams, you certainly want the process and the design engineer involved. You want a process safety engineer. Process safety engineer will take the HAZOP-LOPA analysis and determine what SIL level is required. And you want a process control engineer because they're going to be programming the logic solver.
Okay, thank you. As far as documentation, why is that so important?
Documentation is important so that the safety integrity level is maintained without dispute. So if somebody wants to come in, say you have a SIL 1 sensor, somebody wants to come in and quickly put in a less expensive sensor with no documentation, you could lose your safety integrity level of the whole safety instrumented function. So the documentation is important to go back to when changes are made.
Makes sense. All right, thanks, Doug. It looks like we have one other one here. Why is management of change required for changes to SIS?
For any serious process changes, except for replacement in kind, an MOC should be required, especially for a safety instrumented system. And the reason for this is to ensure that the safety integrity level of the safety instrumented function is maintained and you're getting the same protection as originally designed.
Excellent. Thank you, Doug. Well, it looks like that gets us to those questions, it looks like. Certainly want to thank everyone for joining us for our discussion today covering safety instrumented systems. Should you need any assistance with testing and or process safety support, please feel free to contact us at info-us@sigma-hse.com. We look forward to being a resource to you. Have a great day.
Thank you, Mark. I'd like to thank everybody on the call too for your time and attention. Have a good day.